SUSE has a strong vision for the future of automotive software development. One where we think that lessons can be learned from other industries like the telecommunication industry and implemented for the benefit of car makers and customers. My name is Joachim Joe Werner and I'm the Principal Product Manager for Automotive at SUSE. In the next couple of minutes, I'm going to guide you through that vision. So when we are talking about lessons learned, I mean concepts like continuous integration and delivery. But let me ask, can those concepts, can continuous integration and delivery actually work for cars? Isn't that just science fiction? 67. 67 is the answer to that question. This is the number of over-the-air software updates that a Tesla Model 3 got over just 3.5 years, according to a recent blog post. So frequent over-the-air software updates, feature updates, and bug fix updates are the reality today. And what we are going to talk about here is not science fiction. It's meant to be a wake-up call for the industry. Fortunately, there already is quite some consensus that the future of the modern vehicle is software-defined. What does that mean? Well, at the moment, a car has sometimes over 100 compute units, ECUs, electronic compute units, for all kinds of features like the anti-lock brake system, the park assistant system, or maybe just the controller for your matrix LED headlights. And also, of course, the whole space of infotainment like your radio and music player. The idea of software-defined vehicles is to take all those hardware features and to a large extent centralize them on a central computer. So those ECUs would move as software functions on top of a central high-performance compute cluster. There are two major initiatives working on these problems. One is SOFI and one is the Eclipse SDV. SUSE is a founding member of both. SOFI, for example, the Scalable Open Architecture for Embedded Edge, is aiming to deliver a cloud-native architecture enhanced for mixed criticality automotive applications with corresponding open source reference implementation. And very similar to that, Eclipse SDV is an open technology platform for the software-defined vehicle of the future, focused on accelerating innovation of automotive-grade in-car software stacks using open source and open specifications. And the idea is to develop that in an open and vibrant developer community. Just recently, SUSE also joined another project, Gaia X for Ageda. This is a project that is partially funded by the European Union and the German government. And the idea is to develop a software architecture for the edge device car, one that also looks into topics from the Gaia X space like data sovereignty. And by design, that architecture is meant to be ready for data-driven applications and also for dynamic adaptation, reconfiguration, updating the car over the entire life cycle. So, first of all, before we dive into this, what are the main drivers? Why are software-defined vehicles getting so important? Well, that's the case. The four defining drivers of software-defined vehicles are cars are getting connected. So they're basically mobile devices with the e-call feature, for example, in the European Union, it's mandatory for the car to be able to send an emergency call when an accident happens. Cars are getting stronger and stronger advanced driver assist systems up to the ultimate goal of level 5 self-driving cars. This means a lot more data is produced by all those cameras and sensors in the vehicle that need to be processed. Cars are getting shared. The concept here is to some extent go away from buying cars as major investments to sharing cars in a clever way. Concepts like robo-taxis, for example. And finally, of course, the electrification of the car. All those 4 mega trends lead to more software and more hardware in the car. But of course, there are challenges. So first of all, once the car is full of IT, it has the same challenges with chip shortages, for example, with disruptions in the supply chain. And in the last couple of years, this became really obvious when a lot of cars couldn't be built because just 1 or 2 chips weren't available. But not only chips are short, there's also a shortage in talent. Now that a lot of your car is software defined, OEMs, automotive manufacturers, have to hire thousands of software engineers. When cars get connected, they are basically as vulnerable as your smartphone or mobile device. So cybersecurity is getting really important. And because of the UN regulations 155 and 156, this is now in many countries part of the homologation process of new cars for type approval. Luckily, SUSE has a very strong answer for that kind of cybersecurity problems because we can provide secure and regularly updated software with a secure software supply chain. Just recently, we got our supply chain validated by the SALSA framework. This is what SUSE has been doing for many, many years. So let's look into an industry that has had pretty much similar problems for the last 20 or so years. Just 20 years back, if you looked at a typical cell tower, the telecommunication industry had a very similar setup with lots of dedicated computers. You could think of them as ECUs that all came as black boxes from different vendors with embedded software. They were really hard to update. They were single function or very limited function. And usually when you had to move from, let's say, the 3G standard to the 4G standard, most of the hardware would have to be replaced. Around 2010, the industry started to change that by virtualizing those computers, those special devices as virtual machines on top of more or less off-the-shelf server hardware. This was called network function virtualization. And these days, in the 2020s, the telco industry has gone one step further with an open framework for developing the next generation 5G O-RAN, and also with switching to a setup where basically all the workloads are containers and managed by Kubernetes. Actually, SUSE just recently announced the Adaptive Telco Infrastructure Platform. That's an offering where we take our best products, Rancher Prime, RKE2 Kubernetes, and also SUSE Linux Enterprise Micro, and combine them with best practices for the telco industry. We think that we can do something very similar for the automotive industry, and we've identified 4 main areas. First of all, and that's of course where we have the most experience, the operating system in the vehicle, where to make this software-defined vehicle where features can be added as components, we add a container runtime, we add an orchestrator. Then this has to be augmented by what SUSE can do really well, the secure software supply chain. And for automotive and other embedded industries, we are developing new tools for creating the images that you put on your computers that are more familiar to work with for people who are not coming from a traditional Linux server distribution world. Of course, the computer is only a small part of the offering. The product these days is a combination of services, cloud services, mobile apps, the actual car, lots of data. Data that goes to the car, data that is collected by the fleet of cars, sent to the OEM. For those backend infrastructures, just like we've proven for telco, we think we are a strong partner. We can help the automotive industry building these scalable cloud infrastructure solutions. And finally, the part that's missing is if you want to develop modern car software in an agile way with regular updates, you also have to take care of compliance. And we think the right approach is to embed compliance into your CI/CD process. But let's briefly look into the OS part, the Linux part first. We think that Linux is the perfect match for the challenges of the automotive industry. Linux has a proven track record as being basically the perfect hardware agnostic stack. This helps you with all your chip sourcing problems because you get much less dependent on a single vendor. Linux is the hardware abstraction layer that you need. It delivers on the promise that Java made a couple of years back to develop once and then run on all major platforms. In other words, the OS needs to be a stable platform so that everything else can change. It abstracts away changes in hardware, but it also abstracts away changes in software so that the hardware vendor has an easier time with supporting new software stacks without having to change everything all the time. And of course, open source software in general and Linux boosts your productivity. Because when you use an existing open source software as the base, you don't start from scratch. You start from a huge set of already proven software that is really good at doing a lot of jobs. And if you're missing parts, you can co-develop those. And our recommendation really is for automotive vendors to co-develop most of the non-differentiating software together with other companies. And a lot of the software in the car is basically going to be boilerplate software that customers expect and that are not really relevant for your brand experience, for making your specific brand what it's known for. That way you can save a lot of cost and effort and also make things more secure and safe because you can reuse components that are well tested in new projects, even on new completely different hardware. To get there, there's some work to do, and I'm calling it a 3-step program. The first part, we'll get to that again in a minute, is the centralization that I've mentioned before. Then one thing the industry really has to work on, together with the hardware vendors especially, it's hardware enablement. The way the industry is currently doing hardware enablement is like 20, 30 years back in the data center. Remember when you got a new printer, you got a CD or sometimes even still a floppy disk with a driver, and that driver was never updated. It was built once. Once you wanted to update to a new operating system, you may run into driver problems. And this is basically how BSPs, board support packages, work these days. In the Linux world, in the data center and cloud, it's a very different story. Hardware enablement happens when the hardware is being developed, and it happens in the upstream kernel. So once the hardware is delivered to the customer, the Linux kernel and the driver ecosystem and the tool chain and the compiler, they already know about those features. And companies like SUSE can then maintain and support these stacks for many years for a variety of hardware. So let's dive a bit into centralization. Why is centralization key? Well, obviously, if we have up to 100 and more ECUs in the car, all of them having embedded software, it's very hard to change things. If you have to exchange the hardware, this is really expensive. And sometimes those devices are, in very hidden places in the car. And also, even if the hardware is software updatable, this is sometimes not possible over the air. It's a very time-consuming problem, and you have to do it in the right order and so on. So it's really important to implement that concept that I've mentioned at the beginning of my talk, to bring physical components to software functions that are consolidated on a central computer. Such a central computer has other benefits that I haven't mentioned yet. For example, power consumption. At the moment, some electric vehicles may use between 100 and 300 watts during charging just because of all the computers that are running. With a central computer, you can really use all the modern power saving features and just run the workloads at the clock speed that you really need. That's a great way of saving power. Also, especially when your central computers are redundant, it's very easy to service them. So let's say you have two, call it compute blades, one breaks, you can still drive with the second one just without backups. You can then get the other one replaced. But you can also update them after a couple of years without having to throw away the whole car with a stronger computer. And well, this is all possible through what I'm calling, or the industry is calling, late binding. So you don't develop your software specifically for a specific hardware platform, but against an abstracted interface, basically what the Linux kernel is providing you. So you can even, during the lifetime of a current model generation, switch the hardware to even different hardware architecture, with some retesting, of course, but you don't have to start completely from scratch. Now, the final piece in the puzzle is security and safety. And how do we implement security and safety as part of your software development lifecycle? Just to make sure we understand the definitions here. Security, cybersecurity, is about protecting cars from people, from bad people. So basically making sure cars can't be hacked or attacked. Functional safety is about protecting people from cars. Cars can be pretty dangerous devices, and it's important to make sure they are as safe as possible. So if you look at the CI/CD life cycle, I've deliberately chosen this cycle instead of the usual Unity symbol, because it was much easier to visualize this way. On the dev side, we have planning, coding, building, testing, and then there's the release, deploy, operate cycle, and monitoring. Monitoring is really important, as we'll see in a minute. We think that implementing compliance can already start on the coding side. We can make sure that our policies are part of the code. We basically put our policies, our compliance rules, coding rules into the code repository. We make sure that tests are developed as part of writing the code. And of course, it all starts already by having a solid foundation with pre-built open source software that is already pre-proven by a lot of use, by a lot of testing. We then, of course, follow best practices like ASPICE to the extent possible, because, of course, not everything is possible if you're using pre-existing software. Because of the high functional abstraction that we can achieve if you don't develop against individual hardware targets, we can also do a lot of testing in an abstracted way later, and we'll see that, let's say, in the cloud. And a lot of those modules will be tested once and then can be reused in different scenarios. Yeah, then when you come to building, it's very important to have highly automated build systems. The whole concept of being able to reproducibly build the same software from the same code again and again. SUSE has a very strong tool called Open Build Service, OBS, that we are using both for our community distributions, OpenSUSE, and for SUSE Linux Enterprise. And of course, we also have a lot of pre-built packages that you don't always have to rebuild, and where we can ensure that those have been built according to the highest standards in a reproducible way. And as mentioned before, again, hardware abstraction is much easier that way. We are already building against a lot of hardware targets and can basically prove that the code will work on platform A and platform B. In the build system, you can already run a lot of tests during build. And then after building, you should have a fully automated test system as well. We have OpenQA, for example, and that's what we are using again for OpenSUSE and SUSE Linux Enterprise for all the integration testing. This can be used for functional and also non-functional tests. So you could have tests that just look for compliance goals on the functional safety side, like code coverage for test cases and so on, and run those as part of the testing framework. And you can then run massive tests, if necessary, in cloud-based environments. And the ultimate goal really is to have full stack testing in basically a digital twin of your car. Well, let's kind of skip to the end of the ops cycle. When the software is already in the car, you're going to monitor what it's doing, and you can then take the data that is collected through logging and measuring and improve quality and compliance by augmenting your code build and test phases. That's really the concept that we are going to work on in the next couple of years. So towards the end of this talk, I want to briefly get back to the hands-on stuff that we are doing today, and that's Linux in the car. We now have SUSE Enterprise Linux running in production vehicles, and we are taking the experience from that project and we are building demonstrators. We've started with a Raspberry Pi based car, a small model car, where we're demonstrating A, we can run on ARM, and B, we can show you how you can update parts of the stack and rollback with updating the Linux image, updating the actual compute workloads as containers. The next step was the hypercar demonstrator, the hypervisor car. That's a more complex demonstrator where we are adding more components. We are running a hypervisor, we are running a real-time OS, and we are running 2 Linux instances. And we show how the RTOS can be a watchdog for the 2 Linux instances. Well, the ultimate goal for the next couple of years is to provide an automotive Linux distribution based, of course, on our automotive version of what we call the adaptive Linux platform ALP. This will be developed in the open, and all those demonstrators will be available and more. Just to briefly look into what you can expect from ALP Automotive, and that's just the working title. Name may change. It will be developed in the open, as mentioned. It will come with a software bill of materials, so you can use it in professional projects. It comes with a real-time kernel. It will be as small as possible, but of course not smaller than that. We'll have no GPL v3 software in the runtime stack. And it will be ready for over-the-air updates. It will also support some of the most common workloads, from just plain containers to ROS2 based stacks, and ultimately also, adaptive AutoSAR workloads, for example. You're going to support x86-64 for Intel and AMD, and 64-bit ARM architecture. And it will be ready if you need it to be integrated into a quality management framework. As part of the Ageda project, Gaia X4 Ageda that I mentioned, we are also building more demonstrators where the then current version of the ARM-based Automotive Linux will be part of the overall Ageda demonstrators. Let me finish with a final slide that I think shows you how powerful having Linux in the stack is. You'll be able to develop your software on a laptop, even if you're choosing, for example, an ARM-based Macintosh. You can run it more or less natively with the exact same hardware architecture that's going to run in the car. And you can also use that very same framework in the cloud for testing, because companies like Amazon with AWS Graviton provide ARM-based runtime environments in the cloud. And then in the vehicle, on the actual automotive silicon, you can run that exact same software and hardware as tested. I hope I could show you how we are on the right track for achieving the mission we have for the OEMs. SUSE wants to empower automotive OEMs through the complete life cycle of open source based cloud-to-car software development, so that they can focus on delivering highly competitive driving experiences, not on reinventing software wheels all the time. Thank you for your attention.